Imagine a computer that doesn't think in simple ones and zeros, but instead harnesses the bizarre rules of quantum physics to solve problems in minutes that would take today's supercomputers thousands of years. That's the dream of quantum computing, a technology that could revolutionize fields like drug discovery, material science, and encryption. But here's the catch. We're not there yet. Let's break down why this technology is still in its infancy, what it takes to make it work, and how long it might take to change the world. First, quantum computers aren't just better versions of your laptop. They're built for very specific tasks. Think of them as specialty tools like a scalpel instead of a kitchen knife. For example, they could one day crack complex codes or simulate molecules. Design life-saving drugs, jobs where classical computers hit a wall. For everyday tasks like streaming videos or writing emails, your phone will do just fine. Another big hurdle? Quantum states are incredibly fragile. Particles that power these machines, called qubits, are like soap bubbles. They pop at the slightest disturbance, heat, vibrations, even straight electromagnetic waves. Today's best qubits only stay stable for millionths of a second before they crash. To make matters worse, even tiny errors during calculations can derail the whole process. Fixing these errors requires layers of redundancy, meaning you might need thousands of qubits just to do the work of one reliable, logical qubit. Now, building a quantum computer is like running a science experiment in a high-tech freezer. Qubits, like the ones Google and IBM use, only work at temperatures colder than outer space, just a hair above absolute zero. Cooling them requires massive, energy-hungry refrigerators that guzzle as much power as a few households. And the setup isn't exactly compact. A machine with 50 qubits might fill a room, thanks to the maze of cooling pipes, shielding, and electronics needed to keep it running. Progress is happening, but it's slow. Today's quantum computers are like the clunky, room-sized computers of the 1950s. They have 50 to a few hundred qubits, enough for experiments but not yet practical for real-world problems. Experts estimate we'll need millions of high-quality qubits to unlock breakthroughs like unbreakable encryption or designing super-efficient batteries. Timeline? Optimists say we might see niche applications in 10-15 years, like simulating molecules for new medicines. For quantum computers to upend industries or crack today's internet security, that could take 20-30 years or longer. It all hinges on solving physics puzzles, like making qubits more stable, engineering feats, like building control systems that can manage millions of qubits without errors. Bottom line, quantum computing is a thrilling frontier, but it's a marathon, not a sprint. It's limited by the laws of physics, the complexity of engineering, and the sheer cost of pushing technology to its absolute limits. Now, it remains a tool for labs and researchers, not something you'll see at your local electronics store. The potential is undeniable. If we can tame the quantum world, it might just reshape ours, one fragile fleeting qubit at a time.